Our universe is not a random scatter of stars. It is a colossal architecture of luminous threads, a cosmic web stretching across unimaginable distances. This vast network of filaments forms the fundamental skeleton of everything we see, yet it is built upon profound secrets that defy our current grasp of physics. By the end of this journey, you will understand the 25 greatest enigmas locked within this structure, questions that could redefine our place in the cosmos. We will explore why dark matter remains an invisible ghost and how entire galaxies are merely passengers on these cosmic rivers. What single mystery of the universe do you find most compelling? At the very foundation of this cosmic architecture lies its deepest mystery. How did these filaments, these immense threads of matter spanning hundreds of millions of light years, emerge from an almost perfectly smooth beginning? The early universe was a hot, dense soup, a near-uniform sea of particles. For such a delicate web to form, there had to be tiny seeds, minute wrinkles in the fabric of space and time. These initial density fluctuations were imprinted in the first fraction of a second during a period of hyper-accelerated expansion called cosmic inflation. Think of it like a smooth sheet of rubber being stretched so rapidly that its microscopic imperfections become vast hills and valleys. These wrinkles were the blueprints for everything to come. But blueprints alone do not build a city. This is where the invisible hand of dark matter took over. Dark matter, which does not interact with light but feels and exerts gravity, began to clump around these slight overdensities. Its relentless gravitational pull acted as a cosmic scaffold, drawing in ordinary matter over billions of years. The filaments are the ghostly imprints of that dark matter skeleton. The puzzle for our leading model of the universe, the lambda CDM model, is one of timing and scale. The filaments are simply too vast, and they appeared too early in cosmic history. Their grand structure challenges our understanding of how quickly gravity can sculpt the cosmos from such a smooth initial state. We are left wondering if our models of dark matter are complete, or if some other unknown force helped weave this immense tapestry so swiftly. That invisible scaffold raises an even more profound question. What exactly is this dark matter that dictates the shape of our universe? We know it must exist because we can observe its immense gravitational pull, the force that carved the cosmic web from the primordial void. Yet it remains utterly elusive, a ghost that we cannot see, touch, or trap. Its role is absolutely exclusive. Dark matter alone had the unique properties needed to build the universe's skeleton. Because it does not interact with light or with itself, it could avoid the pressures that would have pushed ordinary matter apart. Think of it like this. In the early universe, ordinary matter was a turbulent, hot gas, constantly buffeted by radiation. But dark matter was a silent, cold sea, unaffected by the chaos. Its particles, moving slowly compared to the speed of light, are what cosmologists call cold dark matter. This cold, calm nature allowed it to respond only to gravity, to clump together efficiently and form the very first gravitational wells, the valleys in spacetime. These wells became the templates for the filaments. The ordinary, visible matter, the stuff of stars and planets, was simply a passenger. It flowed along these pre-existing dark matter channels, cooling and condensing into the galaxies we see today, strung like pearls on the invisible strings of the cosmic web. So why, after decades of searching, can we not directly detect this substance that makes up over 80% of all matter? Our most sensitive experiments, buried deep underground to shield them from cosmic noise, have come up empty. This is not a minor oversight. It is a fundamental gap in our understanding of reality. The dominant component of the cosmic architecture, the very material that gave the universe its form, remains a complete mystery to our senses. What if its nature is so alien, so different from anything we have ever conceived, that our current physics cannot even frame the right question? So if dark matter is the hidden architect, where is all the normal stuff? We are made of ordinary matter, the atoms and particles that form every star, planet, and person. Yet when cosmologists tally up all the visible matter in the universe from the earliest light, they come up startlingly short. A vast portion of it, nearly half, is simply missing. This is the missing baryon problem, and the prime suspect for its hiding place is the cosmic web itself. The theory is elegant. After the Big Bang, all that ordinary matter was swept along the dark matter filaments, but it wasn't all destined to become galaxies. Most of it, in fact, was stretched into a colossal, tenuous ocean of superheated gas suspended within the filaments. Scientists call this the warm-hot intergalactic medium, or the WHIM for short. Imagine a fog so thin, a single wisp of it stretched across the volume of our entire solar system would contain less mass than a small mountain. Yet this fog is unimaginably hot, heated to millions of degrees by the gravitational shock of collapsing cosmic structures. This combination of extreme heat and incredible thinness makes the WHIM nearly invisible. It does not glow brightly like a star. It does not form dense clouds we can easily see. Its detection is one of the greatest observational challenges in modern astronomy. We are essentially searching for a ghostly, superheated vapor that constitutes the backbone of the cosmic architecture. Finding this missing matter would confirm our entire model of cosmic evolution. Its continued absence, however, hints that our understanding of how the universe assembled itself, even from its ordinary components, is still profoundly incomplete. But this warm, thin ocean of missing matter is not static. It is a cosmic river system flowing along the dark matter filaments in a vast and complex cycle that fuels the birth of galaxies. How exactly does this tenuous gas, spread across millions of light years, manage to collect itself and pour into a galaxy to form new stars? The journey is far more violent and chaotic than a gentle stream. As vast flows of intergalactic gas surge along a filament toward a dense cluster of galaxies, they do not glide smoothly. They collide with other flows, slamming into one another at speeds of hundreds of kilometers per second. These collisions create colossal shock waves akin to sonic booms on an interstellar scale. The gas gets violently compressed and heated to temperatures of millions of degrees in a process called shock heating. This is why the filaments glow faintly in X-rays, a testament to this ferocious energy. For the gas to eventually cool and condense into stars, it must somehow shed this immense heat. This is where another layer of mystery unfolds. The gas must radiate away its energy, cooling down over cosmic timescales, but our simulations of this process consistently run into a problem. They predict that gas should cool and flow into galaxies much more efficiently than we actually observe. In our virtual universes, galaxies often become too massive too quickly, forming far more stars than we see in the real cosmos. Something is putting the brakes on star formation. The missing ingredient might be turbulence. Within these cosmic rivers, the flow is not laminar and smooth. It is likely a churning, chaotic mess of swirls and eddies. This turbulence could act as a kind of cosmic insulation, preventing the hot gas from cooling effectively and delaying its arrival into the galactic core. It is as if the fuel lines to the engine of a galaxy are tangled and frothing, regulating the supply. This discrepancy between our models and reality points to a critical gap in what we call baryonic physics. We understand the gravity of dark matter, but we are still learning the intricate dance of normal matter within its grasp. How gas is shock-heated, how it is stirred by turbulence, and how it ultimately cools to spark new stars are processes that remain just beyond our full comprehension, hidden within the faint glow of the cosmic web. This intricate cosmic plumbing does more than just deliver fuel, it actively sculpts the galaxies it feeds. The connection between a galaxy and the filament it calls home is a dynamic and often violent relationship, one that dictates a galaxy's very identity. A galaxy's fate, whether it becomes a star-forming spiral or a quiescent elliptical, is written in the flow of these cosmic rivers. For a spiral galaxy like our own Milky Way, the flow of gas along a filament is relatively gentle and steady. This constant cold accretion provides a renewable fuel source, allowing new stars to form in an orderly disk and maintaining the galaxy's graceful, rotating structure. The spin of the galaxy itself may even be aligned with the direction of the filament, as if the galaxy is a leaf caught in a vast, gentle current. But for galaxies residing at the crowded intersections of filaments, the nodes of the cosmic web, the story is dramatically different. Here, multiple rivers of gas collide and merge in a chaotic frenzy. This environment is one of extreme violence, where rapid, intense bursts of gas inflow can trigger ferocious episodes of star formation, rapidly exhausting a galaxy's gas reserves. Worse still, the gravitational pull from neighboring galaxies in these dense knots can stir up the galactic disk, randomizing the orderly orbits of stars and transforming the elegant spiral into a bloated, featureless elliptical galaxy. The galaxy's own supermassive black hole, fed by the immense influx of matter, can also awaken, blasting the surrounding gas with so much energy that it shuts down star formation entirely. This is the great cosmic paradox. The same filaments that give life to galaxies by feeding them gas can also, under the right conditions, lead to their stagnation and death. Why do some nodes create these monstrous elliptical giants while others nurture serene spirals? The answer seems to lie in the delicate balance between the rate of gas supply and the gravitational turmoil of the environment. It is a balance we can observe in the heavens, but one whose precise rules continue to elude our understanding, hidden within the silent currents of the cosmic web. These ghostly rivers of the cosmic web are not empty conduits. They are laced with invisible force fields, magnetic fields of immense scale and unknown origin. We have detected their faint imprint, a subtle magnetism that threads through the vast intergalactic voids, and their very existence poses a monumental puzzle. Where did these fields come from, and how did they grow to permeate the entire universe? One possibility is as profound as it is ancient. These magnetic fields could be primordial, a fossil relic from the universe's very first moments. In the violent chaos of the Big Bang, phase transitions in the fundamental forces of nature might have imprinted magnetic seeds across the entirety of space. If this is true, then the faint magnetism we detect today is a whisper from a time before the first stars, a permanent feature of the cosmic fabric. The alternative is that these fields were generated much later, woven into the cosmic web by the very galaxies they connect. As galaxies form and evolve, they spew out colossal winds from supernova and active black holes. These galactic outflows, filled with charged particles, could have acted like immense cosmic dynamos, injecting magnetic energy into the filaments. The intense turbulence within the flowing gas of the web could then have amplified these weak seed fields, stretching and twisting them until they strengthened and spread across millions of light years. So which is it, an ancient echo of creation or a later addition from the furious activity of galaxies? The answer holds immense power over our understanding of cosmic evolution. These magnetic fields are far from passive. They can act as a cosmic glue, providing pressure that helps confine the tenuous gas within the filaments, preventing it from dissipating into the void. They are also thought to be incredible particle accelerators. Charged particles like protons and electrons can become trapped by these magnetic field lines, whipping back and forth until they approach the speed of light, becoming the mysterious cosmic rays that constantly bombard our own galaxy. This means the cosmic web is not just a structure of matter, but a dynamic entity that shapes the very energy flowing through the cosmos. The strength and structure of these fields directly influence how gas cools, how cosmic rays travel, and ultimately, how galaxies themselves are born from the flow. Unlocking the mystery of their origin is not just about finding a source. It is about understanding a fundamental force that has silently guided the growth of the universe from its earliest epochs to the present day. These magnetic fields are a later chapter in a story that began in the universe's first fleeting moments. The grand design of the cosmic web, the specific arrangement of its filaments, their lengths and thickness, is a fossil imprint of that primordial era. Every knot where galaxies cluster, every thread stretching across the void, can be traced back to a whisper, a microscopic quantum fluctuation born in the first trillionth of a second. During the epoch of cosmic inflation, space itself expanded at an unimaginable rate, stretching these random quantum jitters from a subatomic scale to a cosmic one. Think of a tiny, random pattern etched onto a balloon. As you inflate the balloon to the size of a city, that pattern becomes a vast, macroscopic landscape. In the same way, the gentle hills and valleys in the density of the early universe were simply those infant quantum fluctuations, magnified to encompass the entire cosmos. They became the gravitational seeds around which dark matter and then ordinary matter would eventually coalesce. The precise statistical properties of the web we see today, the way filaments connect and how matter is distributed within them, are a direct reflection of the specific type of inflation that occurred. It is a cosmic fingerprint. The physics that drove inflation operated at energy scales 1 trillion times higher than anything our largest particle colliders can achieve. We cannot recreate those conditions, but we can read the blueprint they left behind in the architecture of the cosmic web. By meticulously mapping the filaments, measuring their clustering, and analyzing the distances between galaxy clusters, cosmologists are essentially performing forensics on the birth of spacetime. The subtle patterns woven into the web could tell us if inflation was driven by a single, simple field, or if it was a more complex, multi-stage process. They might even reveal the signature of other forces or particles that existed only at that incredible dawn. The cosmic web is therefore more than a structure, it is a living record. Its very geometry is a message from the universe's first instant, waiting to be fully decoded. That ancient blueprint, written in quantum whispers, gave the cosmic web its form, but a deeper puzzle lies in its endurance. How do these threads, gossamer thin on the cosmic scale, withstand the relentless tug of war from the gargantuan galaxy clusters anchored at their ends? It is a structural mystery, the question of what provides the cosmic tension to keep these filaments from simply snapping or collapsing into a string of isolated beads. The most obvious force, the gravity from the clusters, should be tearing them apart. Imagine a delicate thread of silk stretched between two powerful magnets. Left alone, the magnets would pull the thread until it ripped. The cosmic filaments are that thread, and the galaxy clusters are those unimaginably powerful magnets. So why do we see these structures persisting for billions of years? The first answer lies in the invisible scaffold of dark matter. The dark matter within a filament is not a smooth river. It is a vast, coalescing stream of countless microscopic dark matter halos, a swarm of invisible substructures. This swarm provides a kind of internal skeletal strength. The collective gravity of all these tiny, dark clumps acts like a reinforcing rod running through the center of the filament, giving it a gravitational spine that resists total fragmentation. Then there is the internal pressure of the superheated gas itself. This warm, hot intergalactic medium, though incredibly thin, is searingly hot. That heat translates into pressure, a force pushing outward from within the filament. This gas pressure provides a counterbalance to the inward pull of gravity, preventing the filament from pinching off at its thinnest points. But perhaps the most crucial factor is that these are not static cords. They are dynamic conduits with a continuous, slow inflow of matter from the cosmic voids. This steady trickle of new gas and dark matter acts like someone constantly feeding more thread into the line, maintaining its integrity against the forces trying to consume it. It is a perfect and delicate triple balance. The dark matter's gravitational skeleton, the hot gas's internal pressure, and the constant inflow of new material together create a state of stable tension. This equilibrium allows the filaments to serve as the universe's lasting highways, guiding matter for eons. Yet, this very balance is what makes them so vulnerable to disruption. When a galaxy within a filament experiences a violent outburst from its supermassive black hole, that blast can inject enough energy to overwhelm the local gas pressure, potentially severing the fuel line and starving galaxies further down the cosmic stream. The stability of the filament is not a given. It is a continuous cosmic struggle, a testament to the subtle forces that maintain order within the largest structures in existence. This stable tension within the filaments is now challenged by a discovery that seems to defy the very nature of these structures. We have long thought of the Cosmic Webs filaments as serene, flowing rivers of dark matter and gas, moving in a grand, linear procession toward the galaxy clusters. But recent observations suggest something far more dynamic is happening. Some of these colossal threads appear to be spinning. The very idea is staggering. A filament is not a solitary object like a galaxy that can spin in isolation. It is a conduit, a fundamental part of a connected flow, a single strand in a universal tapestry. How could such a thing possibly rotate? The detection is subtle, inferred from the meticulous tracking of galaxy motions within these filaments. Instead of all moving directly along the filament's axis toward the clusters at each end, some galaxies show a slight but consistent drift, a sideways motion that suggests they are caught in a vast, slow whirlpool on a cosmic scale. This motion implies the entire filament, a structure that can span hundreds of millions of light years, may be imparting a gentle spin to the galaxies within it. This rotation presents a profound enigma of angular momentum. In our conventional understanding, objects acquire spin through tidal torques. A proto-galaxy, for instance, starts to spin because the gravitational pull from a neighboring object gives it a slight twist as it collapses. But a filament is not a collapsing object. It is an extended, linear structure, and the gravitational forces from the massive clusters at its ends should be pulling it taut, not twisting it. So where did this rotation come from? One provocative theory reaches back to the very beginning. This spin could be a primordial fossil, an imprint from the universe's birth. Just as inflation stretched quantum fluctuations into the seeds for galaxies, it might have also imprinted a universal spin on the fabric of spacetime itself. These cosmic filaments, acting as the most direct tracers of that primordial geometry, could be preserving that initial rotation, a slow spin that has persisted for over 13 billion years. The alternative is that the rotation is generated externally by the sheer complexity of the cosmic web. A filament does not exist in a vacuum. It is constantly tugged and sheared by the gravitational tides from other nearby filaments and massive voids. This complex network of forces, this cosmic tidal torque, could gradually transfer angular momentum to the filament, setting it into a slow, coherent spin over billions of years. Both explanations challenge the core of our models. If the spin is primordial, it means the universe was born with a fundamental rotation we never knew about. If it is generated by the web itself, then our understanding of how angular momentum works on the largest possible scales is critically incomplete. This faint detected motion is more than a curiosity. It is a clue that the cosmic web is not a static architecture, but a dynamic, swirling entity, and its slow dance may hold the key to one of cosmology's oldest questions. Did the universe itself begin with a twist? This slow, cosmic spin is not the only force stirring the pot within the filaments. A far more violent and immediate form of disruption constantly rages, one that originates from the galaxies the web itself created. The growth of galaxies is not a gentle process. It is a cycle of furious creation and explosive death, and the fallout from these events does not stay confined within galactic borders. It floods back into the cosmic web in a process we call cosmic feedback. The primary engines of this feedback are supernova and active galactic nuclei. When massive stars die in supernova explosions, they do not fade quietly. They blast out titanic shock waves and drive colossal winds of hot, metal-enriched gas that can escape the galaxy's gravity. This material, traveling at thousands of kilometers per second, slams directly into the pristine gas of the filament. The effect is twofold. First, this ejected gas is incredibly hot, injecting immense thermal energy into the filament's interior. This can reheat gas that was on the verge of cooling and falling into another galaxy, effectively putting the brakes on star formation elsewhere in the cosmic stream. Second, these winds are laced with heavy elements: carbon, oxygen, iron, forged in the hearts of stars and scattered by the blast. This is cosmic pollution on the grandest scale. It seeds the entire intergalactic medium with the raw materials for future planets and life, fundamentally altering its chemical composition. But the most powerful feedback comes from the supermassive black holes at the centers of galaxies. When these monsters feed, they become active galactic nuclei, unleashing jets of radiation and plasma that can punch clear through their host galaxy and far out into the filament. These jets are like cosmic blowtorches, capable of carving enormous cavities in the surrounding hot gas. They can drive turbulence, stir the intergalactic medium, and dump so much energy into the system that they can completely shut down the cooling flow of gas for an entire galaxy cluster, starving it of new fuel for stars. The great mystery is quantifying this chaos. Our simulations show that without feedback, galaxies grow too big, too fast. But when we add it in, the results are exquisitely sensitive to the precise details. How much energy is actually injected? How is it distributed? Does it primarily heat the gas, or does it drive turbulent motions that prevent cooling? We simply do not know the exact rules of this cosmic regulation. It is a complex loop where the product, the galaxy, directly influences its own supply chain and the supply chains of its neighbors. This feedback is the missing ingredient that connects the small-scale physics of stellar death and black hole accretion to the large-scale architecture of the universe itself. Without understanding its precise impact, we cannot truly predict the life cycle of a galaxy or the ultimate fate of the cosmic web that cradles it. This cosmic cycle of creation and disruption is set against a far grander and more ominous backdrop. The ultimate fate of the entire cosmic web is being written by a force even more dominant than gravity: dark energy. This mysterious energy, permeating the vacuum of space itself, is causing the expansion of the universe to accelerate. Its influence is not a future event, it is happening right now, and it is slowly but surely unraveling the universe's largest structure. For billions of years, gravity has been the master architect, patiently pulling matter together to form the web's magnificent filaments and clusters. But dark energy acts as a counterforce, a kind of cosmic anti-gravity that pushes space itself apart. In the cosmic tug-of-war between these two titans, dark energy is winning. As the expansion accelerates, the vast distances between the great nodes of the cosmic web will stretch even further. The filaments themselves, those delicate threads of dark matter and hot gas, will be pulled taut. The gentle, steady inflow of matter from the voids that currently feeds and maintains them will gradually slow, then stop entirely. The filaments will begin to starve. Over trillions of years, the accelerating expansion will stretch these cosmic rivers to their breaking point. They will thin out, becoming ever more tenuous until the gravitational bonds that hold them together are overcome. One by one, the filaments will snap. The cosmic web, the grand architecture that has given the universe its structure for billions of years, will dissolve. What will be left is a vision of profound isolation. The galaxy clusters, once vibrant cities connected by luminous highways, will become isolated island universes. They will drift apart in an ever-cooling and darkening void, their mutual recession speeds eventually exceeding the speed of light. This means that from any one island cluster, all the others will vanish beyond an eternal horizon, their light forever too faint and redshifted to ever reach us again. The universe will become a collection of lonely islands, each destined to live out its internal evolution in complete and utter solitude, their glorious past connections severed forever by the relentless push of dark energy. This is the great existential mystery of our cosmos. The same force that allows space to exist is also destined to tear apart its most magnificent creation, leaving behind a silent, dark, and disconnected cosmos. Yet this grand, evolving structure we see today had to have a beginning. The hunt is now on for the Cosmic Web's very first threads, the primordial filaments that emerged from the darkness of the cosmic dawn. This era, just a few 100 million years after the Big Bang, was when the first stars and galaxies began to flicker on, illuminating the infant universe. Finding the filaments from this time is the ultimate archaeological dig into cosmic history, but it is a search plagued by immense challenges. The primary obstacle is distance. The light from these first filaments has been traveling for over 13 billion years to reach us, stretched by the expansion of the universe into the far infrared and radio parts of the spectrum. Furthermore, the hydrogen gas within these early filaments was not hot enough to glow in X-rays like its modern counterparts. Instead, it emitted a specific, faint radio signal with a wavelength of 21 centimeters. This signal is incredibly weak, and over its epic journey, it has been redshifted to much longer wavelengths, where it is drowned out by a cacophony of radio interference from our own galaxy and human technology. Detecting it is like trying to hear a single whisper from across a crowded, roaring stadium. So how do we find these ghostly structures? Astronomers are using the most powerful telescopes as cosmic time machines, looking for the silhouettes of filaments against the even more distant glow of the cosmic microwave background. They also search for the telltale clustering of the very first galaxies, assuming they must have formed along these invisible dark matter threads, tracing out their shape like fireflies on a dark wire. Successfully mapping even one of these primordial filaments would be a revolutionary window into a lost age. The thickness and density of these first threads would tell us about the nature of the dark matter that formed them. Were they thin and wispy or surprisingly robust, their structure would also reveal the influence of the very first stars and galaxies. The intense ultraviolet radiation from these first stellar furnaces would have heated the surrounding hydrogen gas, boiling it out of small dark matter clumps and fundamentally altering how gas flowed into the filaments. By studying these ancient rivers, we could learn what those first stars were like, how they were grouped, and how they began the great work of polluting the pristine cosmos with the first heavy elements. Finding the first filaments is not just about completing a cosmic map. It is about witnessing the moment the universe's skeleton first emerged from the void, setting the stage for everything that was to come. But this grand cosmic map may not be the same in every direction. As we chart the vast filaments and clusters on the largest scales, astronomers have stumbled upon a profound and unsettling mystery. The universe, it seems, might have a preferred direction. This discovery directly challenges one of the most sacred principles in all of cosmology, the cosmological principle. This principle states that on a large enough scale, the universe should look roughly the same in every direction and from every point. It should be homogeneous and isotropic, a cosmos without a center and without an edge. Yet the data tells a different story. Surveys of galaxy clusters and the cosmic microwave background reveal a startling alignment, a cosmic dipole. It is as if the entire cosmic web is slowly drifting in one particular direction through space. One of the most prominent examples of this is the so-called dark flow. Observations suggest that thousands of galaxy clusters are moving coherently toward a single point in the sky, a motion that cannot be explained by the known gravitational pull of any visible structure. It is a river of galaxies on an unimaginable scale, all flowing the same way. What could possibly be tugging on them? The implications are staggering. If this anisotropy is real and not a statistical illusion, it means our universe is not perfectly uniform. there could be a colossal structure beyond our observable horizon, a gravitational anomaly so immense that its pull is felt across billions of light years. Or, even more radically, it could mean that the universe itself is not isotropic, that the fabric of space-time has a fundamental lopsidedness woven into it from the beginning. This would force us to rewrite the textbooks. Our entire understanding of the Big Bang and cosmic inflation is built upon the assumption of isotropy. If that foundation cracks, we may need entirely new physics to describe a universe with a built-in direction, a cosmos that is not the same everywhere you look. Are we seeing a mere fluke, a chance alignment that will vanish with better data? Or is this the first faint hint of a reality far stranger and more structured than we ever dared to believe? This cosmic drift hints at a universe far from uniform, a reality made even starker when we shift our gaze from the dense filaments to the immense emptiness that defines them. The cosmic web is not merely a collection of luminous threads. It is a delicate balance between the dense and the desolate, between the filaments and the voids they surround. These voids are not passive background, they are active, expanding regions of profound nothingness that dominate the volume of our universe. Their relationship with the filaments is a strange and powerful symbiosis. The voids are relentlessly growing, their emptiness stretching the fabric of space within them. This expansion pulls at the filaments, tensioning them like the skin of a drum. It is this relentless pull from the surrounding emptiness that forces the filaments into their characteristic curved and ribbon-like shapes, dictating the grand geometry of the entire cosmic architecture. Without the voids pushing out, the web would not be a web at all, but a formless, lumpy cloud. The gravity of the matter within the filaments constantly fights to pull the structure inward to thicken the rivers. But the expanding voids exert a negative gravitational pull, a kind of cosmic repulsion born from their sheer lack of density. This tug of war determines the final density and fate of the matter flowing within a filament. A filament stretched tightly between two giant, fast-growing voids will be stretched thin, its gas spread out and unable to cool efficiently to form new galaxies. Yet, where the gravitational pull from a massive knot of galaxies at a filament's intersection is strong enough to resist the void's expansion, the gas can compress, triggering furious bursts of star formation. So how do these vast regions of near-nothingness, these cosmic deserts, command such influence over the universe's most dense structures? Their power lies in their collective dominance. They are the majority, and their expansive nature sets the stage upon which all other cosmic dramas must play out. The voids shape the highways of matter simply by being empty, and in doing so, they write the rules for where and how galaxies can ever hope to shine in the overwhelming darkness. These voids may define the web's borders, but the filaments themselves harbor a deeper secret within their own shadowy substance. If dark matter is the invisible architect, what is the true texture of its creation? We have always pictured it as a smooth, featureless sea, a perfect cold dark fluid flowing along these cosmic channels. But what if that picture is wrong? What if the dark matter within filaments is not a uniform river, but a turbulent stream, filled with its own hidden currents and dense, invisible islands? This is the tantalizing possibility that dark matter itself possesses a rich substructure. Within the vast corridors of a filament, there could be countless dense clumps of dark matter, miniature halos that never manage to attract any stars or gas. There could be fine streams, the shredded remnants of smaller galaxies that were torn apart and absorbed by the filament's gravity. These features would be completely dark, yet their gravitational signature would be imprinted on the very shape of the filament. How could we possibly detect such ghosts? The answer lies in the subtle warping of spacetime. As light from distant quasars travels across billions of light years to reach us, it passes through these cosmic filaments. If a filament were perfectly smooth, it would bend that light in a gentle, predictable arc, a phenomenon we call weak gravitational lensing. But if the dark matter is clumpy, if it contains these dense knots and substreams, the lensing effect would not be smooth. It would create a chaotic pattern of tiny, additional magnifications and distortions, like looking through a window made of old, wavy glass. Our most powerful telescopes are now on the verge of detecting these minute fluctuations. Finding them would be like discovering an entire hidden ecosystem within a forest we only ever saw from a distance. It would prove that dark matter is not a simple, featureless substance, but a complex material with its own intricate physics. This complexity could finally reveal the identity of the dark matter particle itself. For instance, if dark matter particles have even a tiny ability to interact with each other, a self-interacting force, this would profoundly affect how they clump. Self-interacting dark matter would smooth out the smallest, densest clumps, effectively erasing them. It would act like a kind of dark friction, preventing the formation of the most extreme substructures. Conversely, if the dark matter is truly cold and collisionless, as in the simplest models, then a veritable jungle of tiny, sharp clumps should survive within the filaments. The detailed morphology of a filament, therefore, becomes a cosmic laboratory. By mapping its gravitational skeleton with exquisite precision, we are not just tracing its outline. We are probing the fundamental nature of 85% of the matter in the universe. We are asking if dark matter is a solo actor or if it feels its own presence in the dark. The answer is written in the invisible, tangled currents of the cosmic web, a hidden language of gravity waiting for us to learn how to read it. These filaments are more than just rivers of pristine gas. They are history books written in a language of elements. Every thread of the cosmic web carries a faint but measurable metallicity, a chemical fingerprint revealing the violent lives and deaths of countless stars. The very iron in your blood, the oxygen you breathe, was forged in stellar furnaces and then violently ejected, finding its way onto these intergalactic highways. This journey of heavy elements from the hearts of galaxies out into the vast intergalactic medium is one of the most poorly understood processes in cosmic evolution. How exactly do these metals escape their galactic forges and permeate the entire cosmos? The primary delivery mechanisms are as brutal as they are effective. Galactic winds, driven by the combined fury of supernova explosions and radiation from newborn stars, act like immense pressure washers. They blast billions of solar masses of metal-rich gas clear out of the galactic disk, injecting it directly into the surrounding filament. This is not a gentle leak, but a geyser of enriched material. In more extreme environments, another process takes over: ram pressure stripping. When a galaxy falls at high speed through the dense gas of a galaxy cluster, it experiences a cosmic headwind so powerful it can literally scrape the galaxy's gas clean out. Think of it like driving a car through a torrential downpour where the rain strips the paint from the hood. The galaxy's precious reservoir of star-forming fuel, now laced with heavy elements, is ripped away and dumped into the filamentary flows. The metallicity of a filament's gas therefore serves as a detailed fossil record. By measuring the abundance of elements like oxygen, carbon, and iron at different distances from galaxies and at different cosmic epochs, astronomers can read this chemical diary. A high metallicity far from any galaxy suggests that powerful winds were common in the past, efficiently polluting the cosmos. A lower metallicity might indicate that feedback was weaker, or that the gas has been diluted by fresh, pristine inflows from the cosmic voids. This record allows us to reconstruct the universe's total star-forming history, not by counting galaxies, but by weighing the scattered ashes of their stellar fires. The ultimate puzzle lies in the efficiency of these feedback mechanisms. How much of a galaxy's manufactured metals actually escape into the web? Our simulations struggle to get this balance right. Too much metal loss and galaxies cannot form new stars efficiently. Too little, and the intergalactic medium remains a barren wasteland, devoid of the materials needed for rocky planets and ultimately life. The cosmic web's chemical enrichment is thus a grand accounting problem, a balance sheet of creation and dispersal written across the largest canvas imaginable. This chemical fingerprint is not the only ancient relic woven into the cosmic web. A far more elusive and pervasive sea of particles from the dawn of time may be subtly tugging at its very threads. Billions of these ghostly particles, known as relic neutrinos, are passing through your body every second. They are a fossil, a direct remnant from the first second after the Big Bang, and they fill every cubic inch of the universe, including the vast corridors of the cosmic filaments. For decades, we thought of them as essentially massless cosmic spectators flying through the universe at nearly the speed of light without any meaningful effect. But we now know neutrinos have a tiny, almost imperceptible mass, and when you have a universe-spanning ocean of them, even that minuscule mass adds up to a gravitational influence we can no longer ignore. Their primary effect is one of cosmic smoothing. In the early universe, these neutrinos were moving so fast that they could not be trapped by the small, weak gravitational wells of the first dark matter clumps. They streamed freely across the cosmos, and this relentless flow had a washing out effect. It suppressed the formation of the very smallest structures, acting like a gentle gravitational pressure that prevented matter from clumping on certain tiny scales. The cosmic web we see today should bear the imprint of this smoothing. The filaments should be slightly less clumpy, with fewer tiny, dense knots of dark matter than there would be in a universe without massive neutrinos. Detecting this specific signature is one of the most ambitious goals of modern cosmology. How do you find the fingerprint of a particle that barely interacts with anything? The answer lies in ultra-precise mapping of the universe's large-scale structure. By creating three-dimensional maps of billions of galaxies, we can measure the statistical clustering of matter with incredible accuracy. We can look for a specific damping, a subtle deficiency in the power of the cosmic web on very small scales. Finding it would not only confirm that relic neutrinos are indeed shaping the cosmos, it would allow us to actually weigh them. The amount of smoothing directly tells us the sum of the masses of all three types of neutrinos. This is a profound opportunity. Our largest particle colliders on Earth cannot measure this total mass directly. The cosmos itself becomes our laboratory, and the grand architecture of the filaments becomes the most sensitive scale in existence. A successful detection would do more than just solve a particle physics mystery. It would prove that even the most ephemeral components of the universe, particles that barely exist in our reality, have been silently guiding the growth of its largest structures since the very beginning. The cosmic web is not just a structure of dark matter and gas. It is a tapestry woven with the gravity of ghosts. The faint chemical fingerprints and ghostly neutrino seas are not the only ancient records held within the cosmic web. There is another, far more intricate archive written in light itself, a phenomenon astronomers call the Lyman alpha forest. To find it, you must look at the light from the most brilliant beacons in the universe, quasars. As this intense beam of radiation travels across billions of light years to reach our telescopes, it does not journey through empty space. It cuts through a vast, tangled network of cosmic filaments, each one a corridor of mostly hydrogen gas. And every time this quasar light passes through a filament, the hydrogen atoms within that filament do something remarkable. They act like a filter, absorbing a very specific shade of ultraviolet light known as the Lyman alpha line. Each filament, depending on its density, temperature, and distance, imprints a unique absorption line at a specific point in the quasar's rainbow-like spectrum. The final result is not a single dark line, but a dense, intricate thicket of hundreds, even thousands, of absorption lines, all superimposed upon one another. This is the Lyman alpha forest, a cosmic barcode etched into the light of every distant quasar. Decoding this barcode is one of the most powerful tools we have for studying the cosmic web, but it presents a monumental puzzle of its own. Each absorption line tells us a little story. Its position reveals the redshift of the gas and therefore its distance from us. The width of the line tells us the temperature of the gas and the velocity of its internal motions. The depth of the line reveals the density of the hydrogen. A deep, dark line means a dense, cold cloud. A shallow, broad line signifies a warmer, more diffuse patch of gas. The challenge, the true mystery, lies in the inversion. We are looking at a single, one-dimensional skewer through the universe. We have a complex list of densities and velocities, but we do not know how they connect in 3 dimensions. It is as if we are trying to map the entire road system of a continent by studying a single, randomly drawn line on a map. We can see every town and curve along that one line, but we cannot tell how those towns connect to other roads beyond our narrow view. This is the central problem of the Lyman alpha forest. A single filament will be intersected by the quasar's line of sight at one specific point, but we have no way of knowing how long that filament is or in which direction it curves away into the darkness. We cannot tell if 2 adjacent absorption lines in the spectrum come from 2 separate, small clouds or from different parts of one enormous, swirling river of gas. The data is a magnificent yet maddeningly compressed projection of a 3-dimensional reality. To overcome this, astronomers must perform a kind of cosmic tomography. They must observe not one, but thousands of quasars, each one providing a single needle-thin core sample through the universe. By combining all these skewers, they can statistically reconstruct the 3-dimensional sponge-like structure of the cosmic web. They can begin to see where the filaments connect and how the gas flows between them. The ultimate goal is to move beyond just mapping and to understand the physics within these filaments. The subtle shapes of the absorption lines are a sensitive probe of the gas pressure, the intensity of the ultraviolet background radiation, and even the potential presence of that warm, hard-to-find missing matter. The Lyman alpha forest is therefore a paradox. It is both an incredibly rich source of information and a complex cipher that requires the collective light of thousands of quasars to solve. It is our most detailed window into the diffuse anatomy of the cosmic web, a view that reveals the universe not as a collection of isolated islands, but as a single, breathing, interconnected whole. This cosmic coordination extends to the smallest galactic scales, revealing a puzzle that strikes at the heart of how galaxies assemble. Look at our own Milky Way and its neighbor Andromeda. Their satellite galaxies, these smaller stellar companions, are not scattered in a random, spherical cloud as our best simulations predict. Instead, they are often arranged in startlingly thin, rotating planes like flies circling a dinner plate. Even more curiously, these vast galactic disks frequently appear to be aligned with the very cosmic filament that feeds the central galaxy. It is as if the great river of the cosmic web does not just deliver the raw materials, it also imparts a sense of order, a directional memory that persists for billions of years. This is a profound challenge to the standard model of cosmology. In a universe dominated by cold, collisionless dark matter, the process of hierarchical merging should result in a chaotic, swarm-like distribution of satellites arriving from all directions. The fact that we see such structured planes suggests a fundamental piece of physics is missing from our virtual universes. One compelling theory points directly to the filamentary inflow itself. As gas and dark matter flow along the cosmic filament toward the growing central galaxy, this flow carries with it a specific, coherent angular momentum. This isn't the spin of the filament itself, but the spin imparted to the region that will become the galaxy and its surroundings. The infalling material prefers to arrive along a specific plane defined by this primordial torque, and the satellites, both the ones that form in place and those that are captured, are naturally shepherded into this preferred orbital plane. They are like leaves caught in a vast, slow whirlwind, their motion dictated by the original spin of the cosmic river that brought them here. This would naturally explain the alignment with the larger filament. However, some of these planes are so extremely thin and long-lived that they stretch this inflow model to its limits, hinting that the dark matter halo itself may have a more complex, flattened shape that constrains the orbits, or that the satellites we see are not random acquisitions but the remnants of a single, larger galaxy that was torn apart along that specific path billions of years ago. This cosmic choreography, from the largest filaments to the smallest orbiting dwarfs, suggests an unexpected layer of order in a universe we thought was built on chaos. Why does this structure persist, and what does it tell us about the true nature of the dark matter that must allow for it? The silent, aligned dance of satellite galaxies may be a quiet rebuke to our simplest models, a clue that the final word on cosmic structure is yet to be written. This intricate cosmic web, with its turbulent rivers and colossal magnetic fields, may also be the most powerful engine in the universe. Those same shock waves that heat the gas within the filaments are capable of something extraordinary, accelerating subatomic particles to energies that dwarf anything we can create on Earth. These are ultra-high energy cosmic rays, single protons or atomic nuclei that carry as much kinetic energy as a well-thrown baseball, all compressed into a single, invisible speck. For decades, their origin has been one of the greatest puzzles in astrophysics. What natural phenomenon could possibly launch a particle to such an insane velocity? The prime suspect is now the cosmic web itself. The mechanism is a cosmic version of a process we use in particle colliders called Fermi acceleration. Imagine a charged particle like a proton trapped within a filament's magnetic field. It bounces back and forth, a microscopic pinball between invisible walls. Now picture a colossal shock wave born from the collision of two intergalactic gas flows rushing through this magnetic maze. When the particle encounters this moving shock front, it gains a tremendous boost of energy, much like a tennis ball gains speed when hit by an oncoming racket. The particle can be scattered back across the shock by turbulent magnetic fields, only to be hit again and again. With each crossing, it gains more energy, surfing the shock wave until it is finally flung free at nearly the speed of light. The scale of this process is almost incomprehensible. The magnetic corridors within a filament can stretch for millions of light years, providing an unimaginably long acceleration path. The shock waves that power it are generated by the gravitational collapse of entire cosmic structures, releasing energies that make supernova look like firecrackers. This natural accelerator operates with a power that our Large Hadron Collider, for all its sophistication, cannot hope to match. It can propel particles to energies 1,000,000 times greater. Yet, this elegant theory faces a serious challenge. A proton traveling across such vast distances should be slowed by interactions with the cosmic microwave background radiation, the leftover glow from the Big Bang. There is a theoretical limit to how far such an ultra-high energy particle can travel, known as the GZK horizon. If these cosmic rays are coming from filaments billions of light years away, they should have lost their energy long before reaching us. Their detection on Earth, therefore, implies they come from relatively nearby within the cosmic web, from filamentary structures within our own local supercluster. But if that is the case, why do they seem to arrive from random directions in the sky, with no clear, bright source to pinpoint? It is as if the universe's largest particle accelerator is both incredibly powerful and perfectly camouflaged, hiding in the faint, diffuse glow of the cosmic rivers that weave the universe together. This grand cosmic engine, capable of hurling particles with unimaginable force, is built upon a foundation we have always taken for granted, the unshakable law of gravity as described by Einstein. But what if the cosmic web itself is whispering that this foundation might have a crack? The precise way galaxies move within these vast filaments presents a subtle yet persistent puzzle. According to our standard model of cosmology, which pairs Einstein's general relativity with dark matter, the gravitational pull within a filament should impart very specific velocities to the galaxies flowing along it. Yet, when we observe these motions, we sometimes find slight discrepancies, small but consistent deviations from what the theory predicts. These anomalies have led some scientists to propose a radical alternative, that our theory of gravity itself is incomplete. Perhaps there is no dark matter at all. Instead, gravity might behave differently on the immense scales of galactic filaments than it does within our solar system. This idea is the core of modified Newtonian dynamics, or MUND, and its more complex relativistic cousins. These theories suggest that the force of gravity does not fade as quickly with distance as Newton and Einstein decreed. In regions of extremely weak gravity, like the sparse territories within a cosmic filament, a slight modification to the law could mimic the effects of an invisible missing mass. If such a theory were correct, it would predict a distinctly different cosmic web. The filaments might be thicker or thinner. The way galaxies move within them would follow a new set of rhythmic rules. The delicate balance between the pull of gravity and the push of dark energy would be recalibrated, potentially altering the entire timeline of cosmic evolution. The cosmic web, therefore, becomes the ultimate laboratory. It is a single structure that encompasses all environments, from the dense clusters where Einstein's laws are confirmed, to the vast, low-density filaments where alternative gravity would make its presence known. By mapping the web in exquisite detail, by measuring the precise orbits of thousands of galaxies within these rivers, and by weighing the filaments through gravitational lensing, we are conducting a direct test. We are asking the universe to show its hand, to reveal whether the ghost of dark matter is real, or if we have been misreading the laws of gravity all along. The answer is not yet clear. The data is painstakingly difficult to collect and the signals are faint, but the mere possibility forces us to confront a breathtaking idea that the largest structure in the universe might be holding the key to one of the most fundamental questions in all of physics. What if the cosmos is not governed by the gravity we know, but by a deeper, more complex force waiting to be discovered in the silent flow of its great rivers? The universe's grand design might be more than just a structure. It could be a message. Every twist in a filament, every gaping void, and every clustered node in the cosmic web represents a choice, a specific configuration that encodes a staggering amount of information about how our reality came to be. This leads us to a profound question. Is this intricate network the most random, disordered arrangement possible for the matter in the cosmos, a state physicists call maximum entropy? Or is its specific, spider-like pattern a deliberate and information-rich fingerprint of the universe's birth and the laws that govern it? To understand this, think of two different libraries. One library has had all its books thrown into a giant, chaotic heap. This is a high-entropy state. It is maximally disordered, and it tells you nothing except that a mess was made. The other library has every single volume meticulously organized and shelved according to a complex but logical system. This ordered state is low in entropy, and its very structure is packed with information. The cosmic web presents us with this exact puzzle. If it is a high-entropy heap, then the universe has reached a kind of gravitational equilibrium. Its matter spread into the most probable, featureless state allowed by gravity and dark energy. But it does not look like a heap. It looks organized. Its specific pattern of connections seems to hold a cosmic memory. The precise spacing of galaxy clusters, the characteristic thickness of the filaments, the statistical distribution of the voids, all of these details are not random. They are a direct output of the initial conditions set by inflation and the specific nature of dark matter and dark energy. In this view, the web is a colossal archive. Its geometry stores data about the mass of the neutrino, the strength of dark energy, and the quantum seeds from which it all grew. We are only just learning how to read this archive. The great mystery is whether we are seeing the final, fading whisper of that initial information as the universe marches toward a true heat death, or if this complex web is itself the universe's way of writing its own history across the canvas of space and time, a story we have only begun to decipher. Every map of the cosmos is drawn with a flawed lens, our own. The magnificent three-dimensional charts of the cosmic web we so confidently study are not direct photographs. They are reconstructions painstakingly assembled from billions of individual measurements, and each one carries the hidden fingerprints of our own limitations. The primary tool for this cosmic cartography is the Galaxy Redshift Survey. We measure a galaxy's redshift, the stretching of its light toward longer, redder wavelengths caused by the expansion of the universe, and use that to estimate its distance from us. This method builds the entire vast depth of the map, but this foundation is built on a critical assumption that a galaxy's motion is dominated solely by the smooth, serene flow of the cosmic expansion. This is simply not true. Galaxies are also falling. They are plummeting along the cosmic filaments toward the immense gravitational pulls of clusters and knots in the web. These peculiar velocities, these local rivers of motion superimposed on the grand Hubble flow, create a dramatic illusion known as redshift space distortion. When we see a cluster of galaxies on our map, they do not appear as a perfect sphere. They are stretched out, elongated into long, finger-like structures that seem to point directly back at us, an effect whimsically called the fingers of God. This happens because the galaxies at the front and back of the cluster are moving rapidly within its gravitational grip, and we mistake that internal motion for extra distance, smearing the cluster along our line of sight. Conversely, on the vast, flat sheets of the cosmic filaments, the coherent flow of galaxies along the rivers creates the opposite illusion. The filaments appear compressed, squashed into sharper, denser pancakes than they truly are, because the shared flow of galaxies makes them seem closer together in redshift space than their real positions in the universe. Our map is a funhouse mirror, distorting the true proportions of the cosmic architecture. But the distortions do not end there. Even our most ambitious surveys can only see a limited slice of the sky. The geometry of the survey itself, the specific patches of the universe we choose to point our telescopes toward, carves out a window. We are not mapping the entire globe, we are mapping a single continent and hoping it represents the whole Earth. Vast structures could easily lie just outside our field of view, their gravitational influence bending the web we see in ways we cannot account for. The most profound bias, however, may be the most fundamental. The cosmic web is built from dark matter, but we map it using the galaxies made of normal matter. We assume that the glowing galaxies trace the outline of the invisible dark matter skeleton, that they are faithful lighthouses perched on the hidden shores. This is a dangerous assumption known as galaxy bias. Do galaxies form equally in all parts of the dark matter web? Or do they prefer the very densest knots and the very thickest parts of the filaments, leaving the fainter, more tenuous strands of the web dark and unmapped? It is entirely possible that what we call the cosmic web is merely the well-lit metropolitan districts of a much larger, darker and more extensive country that remains almost entirely uncharted. Our entire understanding of the universe's structure, from the timing of its formation to the strength of dark energy, is filtered through these layers of distortion and bias. The grand map we hold in our hands is not the territory. It is a brilliant, flawed, and human interpretation, a whisper of the true cosmic architecture filtered through the noisy static of our own limited perspective. Our universe's unique cosmic blueprint might not be the only one. The specific pattern of its filaments and voids, the precise statistical signature of its grand design, could be the ultimate clue that we are living in just one bubble in a frothing sea of multiverses. This idea stems from the theory of eternal inflation, which suggests that the rapid expansion of space-time did not happen just once, but is ongoing in a vast metastable landscape. In this picture, our entire observable universe is a single bubble that nucleated out of this eternally inflating background, like a single droplet condensing from a superheated steam. Within each bubble, the inflationary field collapses, releasing its energy to create a hot Big Bang and a new universe. But here is the critical part. The properties of that bubble, including the very laws of physics within it, are determined by the specific way the inflationary field settled into its lowest energy state, its vacuum. This settling process, known as the field's roll down the potential hill, is what imprinted the initial quantum fluctuations, the wrinkles that became our cosmic web. The exact amplitude and shape of that primordial power spectrum, the blueprint from which every filament and cluster grew, is a direct reflection of that particular vacuum state. So, the web we see is not a universal constant. It is a local artifact in another bubble universe with a slightly different vacuum. The inflationary field would have settled differently. The initial quantum jitters might have been stronger or weaker. The gravitational seeds might have had a different character. The cosmic web in that other universe could be radically altered, its filaments far thicker and more numerous, or perhaps so faint and wispy that large-scale structure never fully formed. The constants of nature we take for granted, the strength of gravity, the mass of the electron, even the number of spatial dimensions could all be different. In some bubbles, the forces might be so weak that atoms never coalesce. In others, gravity might be so strong that the entire universe collapses back on itself in a fleeting instant. Our cosmic web, therefore, is more than a structure, it is a selection effect. We can only observe a universe capable of producing us. The fact that we see a web with filaments robust enough to funnel gas and form galaxies, yet not so dense as to immediately collapse into a swarm of black holes, may be no coincidence. It is a universe finely tuned for complexity, and the specific statistical properties of its web are the signature of that tuning. The great and humbling mystery is this: the majestic cosmic architecture we have been mapping may be utterly ordinary in the grand scheme of things, just one possible outcome in an infinite ensemble of realities, its unique pattern a quiet testament to our own particular place in a much vaster and stranger cosmic landscape. Even the grandest cosmic structures may have a voice. The vast filaments and clusters of the cosmic web are not silent, but are constantly in motion, a slow and stately dance governed by gravity. These motions, the mergers of entire galaxy clusters and the chaotic orbits of supermassive black holes within them, do not just create a spectacle for our telescopes. They ripple the very fabric of spacetime itself, generating a faint, universe-wide sea of gravitational waves. This is not the sharp chirp of two stellar mass black holes merging, a signal that lasts for mere seconds. This is something far more profound and subtle, a stochastic gravitational wave background. It is a low-frequency hum, a cosmic symphony composed of countless overlapping signals from every massive structure in the universe, all blending together into a permanent, whispering roar. To our current detectors, this hum is completely inaudible. It is 1,000,000 times lower in frequency than the waves LIGO can hear, with wavelengths so long they could span entire solar systems. But future observatories like the Laser Interferometer Space Antenna, or LISA, are being designed specifically to listen to this cosmic bass note. LISA will consist of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart, connected by lasers. Passing gravitational waves will ever so slightly stretch and squeeze the space between these spacecraft, and by monitoring these tiny changes with phenomenal precision, we will finally tune our instruments to the universe's fundamental frequency. Decoding this background hum will open a completely new window onto the cosmic web, one that is independent of light. It will reveal a hidden history of violence and growth that our telescopes have missed. Every supermassive black hole binary system, sluggishly circling each other in the heart of a galaxy, emits a steady, low-frequency gravitational wave as it orbits. The combined signal from millions of these binaries across the universe forms a major part of the background chorus. By listening to its specific properties, we could trace the entire growth history of these cosmic monsters, understanding how they grew so large so quickly by merging with others along the cosmic filaments. But perhaps the most exciting source is the cosmic web itself, the relentless flow of dark matter and galaxies along the filaments, and the occasional catastrophic collision of entire clusters at the web's nodes must also generate their own unique gravitational wave signature. This would be the sound of the large-scale structure evolving, the deep groan of spacetime under the stress of its own immense architecture. Detecting this component would allow us to probe the dynamics of the web in a way that is impossible with light, revealing the strength of the gravitational fields within the filaments and the true violence of their assembly. We would no longer just see the cosmic web as a static map. We would hear it as a living, breathing, and dynamic entity, its deepest rhythms telling a story of construction that began billions of years ago. These 25 enigmas weave together into the grandest unsolved story of all. From the invisible ghost of dark matter that built the cosmic scaffold to the warm, thin ocean of missing atoms hiding within it. From the violent feedback of black holes that regulate star formation to the slow, cosmic spin of filaments that defies explanation, we have traced the magnetic fields threading the void and heard the faint gravitational hum of the web's very structure. We have confronted the possibility that our map is an illusion, our gravity is wrong, and our universe is but one bubble in an infinite multiverse. Each mystery is a locked door. Behind one lies the true identity of the universe's dominant material. Behind another, the origin of the very first galaxies. Another door might conceal the final fate of all structure, a silent, dark dissolution driven by dark energy. Yet these are not merely gaps in a textbook. Every unanswered question is a potential key, a thread that, when pulled, could unravel our current understanding and reveal a deeper, more breathtaking reality. The cosmic web is more than a structure in space. It is a living conversation between the laws of physics and the history of everything, and this conversation is far from over. So we turn this final question to you. As we stand before this tapestry of mysteries, which one captures your imagination the most? Is it the hunt for the first filaments from the cosmic dawn, the eerie coherence of the dark flow, or the profound idea that our entire universe is a single, select piece of a vast multiverse? Share your thoughts in the comments below, and if you are ready to continue exploring the frontiers of space and time, subscribe for more journeys to the very edge of understanding.